Hi there, this is Unit 5, Topic 2. Last we talked about how to represent data with a graph. Now we're going to talk about the basics of graph theory. We're going to go through mostly definitions in this document and then go to the example homework problems to go through some hands-on. So in the previous topic, we briefly covered the terms vertex and edge. We will get into more depth regarding these terms. Recall the first examples consisted of vertices and edges. A vertex represented an intersection or a location such as a school or business. Remember, we would look at a map and then draw that map as a graph, and the intersections would be a vertex. An edge connects two vertices. Edges can serve as a physical connection like streets between two buildings or locations. Again, that map example is a good way to relate this. When you have a street in between two intersections, that would be an edge. Any two vertices connected by an edge is called adjacent. So for example, if you had, let's look real quick. We had these two, oops. If we had two vertices and they were connected, those would be adjacent because they're connected by an edge. Let's go down a little bit more. The degree of a vertex refers to how many edges are meeting a vertex. It is possible to have a degree of 0. So when we say edges are meeting a vertex, we mean lines coming out of these dots, basically. So here's a vertex that has no edges. That means it has a degree of 0. Here's one vertex with one edge. That means it has a degree of 1. And here we have a degree of 2. There's 2 edges. Like an example, let's just look real quick. Here we have A. The degree of A is 2 because there's two edges coming off of that vertex. The degree of B is 1, 2, 3, 4. The degree of C is 1, 2, 3. Again, we'll go through some more examples of that later, but that one's pretty straightforward. Paths and circuits. The way to think of this, if we're looking, remember back to the map example that we'll refer back to. It's like if you were to say, what's the shortest distance between A and B? That would be a path. Not necessarily the shortest, but it's just a path between two vertices. So the above figure is an example of a path. Paths usually are between two vertices. Edges and vertices cannot repeat. The example of a path above is one of many. Let's say, for example, we still wanted to look between the vertices A and M. We could go A to E to J to K to L to M. That's still a path. It's a different path. So just because there is a path, it doesn't mean it's unique or it's the only one. In a circuit, vertices can repeat. So a circuit is defined as it's a type of path. So in a circuit, vertices can repeat. A circuit is a path that begins and ends at the same vertex. So in this example, if we were to go up here and say A to A, and we went A to E to J to K, and I went all the way around in a big rectangle, that would be a circuit because it started and ended with the same vertex. Note, edges do not repeat. They do not repeat. So you can't go A to E to F to K, back up to F. You cannot repeat the edges. Two circuits are the same if they start at different vertices but go through the same vertices in the same order. So let's say, for example, here's a circuit, right? Let's say we start at A, we go B, F, G, all the way around back to A. Now that's one circuit. Let's say now we start at B and go F, G, L, K, J, E, A, back to B. That would be considered the same circuit because even though we started at different vertices, we went through the same vertices in the same order. All right, now connected and disconnected graphs. A graph is connected when a path can be drawn from any vertex to another another typo. Here we go. Sorry about that. Oops. All right, let's say this again. A graph is connected when a path can be drawn from any vertex to another vertex. When you can't connect two vertices, then the graph is disconnected. So here's an example of a disconnected graph. See, I could not draw from this vertex to this vertex because there's nothing connecting these two. It would be considered a disconnected graph. Here's some examples. Which of these are connected? This is not connected because there's some vertices that I can't reach. All right. This one is connected because I could reach every vertex from another vertex because all of them, I may be repeating edges, but there is a path there. Now, this one is also disconnected because there's this path, there's missing paths right here where I can't reach those different vertices. All right, so those are the different definitions. So just to reiterate, we talked about the degree of a vertex. We talked about a path and a circuit and disconnected and connected graphs. So let's go ahead and look at some examples. All right, so here we have what are the degrees of vertices R, S, and T below. So R is right here, and we have 2 vertices. So we know that R is degree 2. So that right now we know we're looking at one of our first 3 options. S has a degree of 0. There's nothing connected. So this is also a disconnected graph because there's a vertex out here that's all by itself. So I already know that this is the answer because it's the only one. Oh wait, excuse me, T also has an option right here. So let's see, T has a degree of 1. So that gives us this one. So R has a degree of 2, S has a degree of 0, and T has a degree of 1. So let's take a look. Great work. All right, next question. Is the following graph connected? And if not, how could you make it connected? So in this one, it's actually connected. Even though this A and D aren't connected, I can still take a path from every vertex on here to another vertex. There's no vertex that's unreachable. So the graph is connected. In the graph below, which vertex is adjacent to vertex D? Remember, adjacent means that it's connected by an edge. So let's see, it looks like vertex D is only connected to C. It's not connected by an edge to A or B. So the answer should be C. Oops. Write only the letter of the vertex, or if there are no, write none. Okay, so let's write C. Submit. Correct, you nailed it. How many circuits are in the graph below? Remember, a circuit is when we start at one vertex and end at that same vertex without repeating any of the edges. So let's take a look real quick. We have, well, let's go ahead and draw it on here so we can take a better look. So let's see, we've got, I'll make a better start. Rectangle. Once I draw it, I'll show you guys the screen. So we have A, B, C, D. All right, so our first path would be this, right? B, C, D, back to B. Our second circuit would be A, B, and remember, it's the same. We're not going to count it going different directions because it's the same, okay? And then we have the outer one, that circuit. So there should be 3 circuits. All right, 3. Yep, that's right, keep it up. Is the following graph connected? And if not, how could you make it connected? Well, can I reach every vertex from another vertex via an edge? No, I cannot because A is not connected to C, nor is B connected to C. So the graph is definitely disconnected. So we know that first option is not for us. It's going to be one of the other ones. Now, you can do it by either connecting A to C or B to C, right? So let's see what we have here. Ooh, new vertex B. The graph is disconnected. It can be connected by drawing an edge from B to a new vertex D. Nope, we do not want to introduce a new vertex. We want to make sure this C is connected. So again, this other option talks about a new vertex. The graph is disconnected. It can be connected by drawing an edge from B to C. Once we connect B to C, then C can go to B to go to an A can go to B to go to C. So now we would all be connected. Great work, that's correct. All right. Based on the following graph, which of these statements is true? So let's see, it says every vertex has degree 3, degree 4, degree 6, or degree 5. Well, we know from that every one of them has the same amount of, or the same degree, which means the same number of edges coming off it. So we really just have to go to 1 and count. We have 1, 2, 3, 4, 5 coming off of X. And just for double checking, even though we know that's correct as 5, let's check for U. 1, 2, 3, 4, 5. So Every vertex has degree 5. Great work, that's correct. And just as an aside, I know this is going to sound a little nerdy, but this is one of the things I love about math, and my graph theory is kind of cool. You can have this thing with all these different shapes, and it actually could represent something in the world. There's all sorts of really cool stuff about math and nature. Example, Fibonacci sequence. Something I'll talk about a little bit later, where a certain pattern of, in nature, for example, sunflowers and certain seashells all follow this pattern. So it's pretty cool to see this pattern representing something. This is the last problem we're going to cover. In the graph below, which vertex is not adjacent to vertex K? So remember, adjacent means that it's connected by an edge. So here we can see that G, F, H, and J are all connected. Looks like I is the only one that's not adjacent to K. That means it does not have a direct edge connecting it. So we're going to put I, submit. Well done. All right, that covers Unit 5, Topic 2. If you have any questions about that or anything else, let me know.